So let's continue with the nonlinear optimization. Today we will see a different family of methods. These are a little bit more focused on specific problems. And we will start presenting these proximal and operator splitting algorithms using an example. So we will use lasso, that is a well-known technique to make regression. And the point is to find some model X such that X measured. So this is theoretically, let's put it in some context that you. So let's say that you have a set of points. So you have X, Y, and you have some points here. You have something like that. So X is defining this part X of W, so F of W of X. This is a vector, but I cannot represent vectors. Okay? So we want this to be Y. So you want F of W X minus Y squared minimum for all points. So this is what you want, and this would be the measurements. And for some specific models, this is a linear transformation. So this thing here becomes AW. So W are the weights that you, or the parameters that you can control here to look like the observations you have. So in many problems, we have this kind of structure. So we have a linear model, so a linear transformation between your weights. Here the X is are the parameters of the model. So in my example, it was W. WA must be equal to some measurements. And then we have some penalization on the W, because we don't want the W to do overfitting. So we penalize it, and you have to find this lambda that controls the trade-off between data fidelity and your prior on the model. And typical penalizations, we have already seen these. So typical penalizations are, let's penalize this problem. So if we want to penalize this problem, then you have to add something on our W. So this is called Tikhonov. Penalization. And this one is the last one. So L2 norm or L1 norm. The last one is so the whole problem is larger. So, and the difference is this thing. So this norm here, this norm is the sum for all the weights squared. This one here is the sum of all the norms in absolute square. So if you think of how do they different regions look like? So let's say I look at all the set of all weights such that the norm of that weight, the L2 norm of that weight is smaller than some radius. So how does it look like? If this is my plane of weights, this is a square, this is a circle. Okay? So it is a circle of radius r. Okay, now let's think of this one. So let's think of what is the shape of the region such that the norm, the L1 norm of those weights is smaller than R. And it is this one. This is R, this is W, and this is R. So they look differently. And the effect on regression is this one. The effect on regression is this. So let's say that you have some goal function like this one, and you are constrained, somehow you're trying to reduce the norm of your weights as much as you can. So that means constructing balls of these different radii that grow, and you must have a balance between the radius of the ball, that is what you have here, and the cost that you have in the goal function. So these kind of weights, they will have a little bit of θ1, a lot of θ2. But you have information distributed over all parameters, so all theta's have some value. But if you use this kind of balls, so this kind of balls tend to have the maximum at some location that has very few theta's activated. So here you have information only in θ2, and θ1 is 0. So that probably, in terms of explanatory power, it is not as bad as this one. So it is probably the cost function at this location will be very similar to the cost function in this location. Actually, as it is drawn, here you have the isolines of equal cost. So in principle, in this example, they have the same cost. This one and this one, they're in the same isoline. So that means that they have the same cost. So with the same data fidelity, you have two different models. One of them has the information distributed over all parameters, but with only a few of them being very significant, but still you have non-zero values. This one has the same explanatory data fidelity term, but most of the parameters are 0. So this L1 penalization tends to make the model parameters to go to 0. Okay, so this is Lasso. And let's see how to solve this kind of problems. So in this particular case, so you have two parts. So the data fidelity term and the penalization. So in general, they are, so these kind of methods we are seeing today that apply to problems in which you have minimum of f of x plus g of x. And this one is a smooth. And this can be whatever. So this can be a smooth or non-smooth. Smooth means differentiable. So how to handle that? So with the smooth part, you can compute gradients, no problem. So compute the gradient of this, that is this one. With the non-smooth part, we will use, instead of the gradient, because at some points it is not differentiable, we will use what is called the proximal operator. So the proximal operator, so you see this part here is just a standard gradient descent. So you have a current solution and you apply a gradient descent. But then you project it to kind of feasible region. Here it is not feasible, but it is not a constraint problem, but we followed yesterday a kind of similar approach. So it is not projecting onto a feasible region, but it is projecting it onto a ball. And this projection here is this one. So it is parameterized by lambda, and you are projecting a vector v. And then for every component of v, what you do is, if v is larger than lambda, it is v minus lambda. If v is smaller than lambda, minus lambda, it is vi plus lambda. So actually this projection operator looks like this. So you have B, you have the projection of V, and it is this function. So this is lambda, and this is minus lambda. Okay, so if you are in this area, and this lambda can be, you can imagine it is a relatively small region, so you set it to 0, and otherwise you subtract lambda. And somehow the effect of this, you can imagine if you go with this vector, you go to the projection operator, the long component, the last component will survive, but the small component, this small one, will not survive. So it will be set to 0. And then you are back into this case. And you will iterate. So it is not that you will keep the projected vector, but you are updating with the gradient descent. So at the end, it will tend to make the components that have a small value in the least squares, it will be, or in the Tikhonov regularization, they will tend to go to 0. Okay, and this is another way of writing that. Any question? No? Okay, another approach to do this is this one. So we have the typical setup in which we have the smooth part, the data fidelity part that typically it is least squares, but you can put whatever there, and the regularization. And one of the interesting, probably you are not in image processing, but in image processing, this total variation is one of the important regularizers. And it tends to make smooth images. So what we will do is what is called this variable splitting. So we will split the problem into parts. So you see it is very similar to this one. So it is just the same, but now we have two variables, and one of the second variables will act as a constraint. And actually in ADMM, that we will see the next day, we use the same, it is used the same trick. Okay, so the thing is that now we have a constraint problem. So if we have a constraint problem, what we can do is to put this constraint through a Lagrangian, so or through a penalization. So in this penalization, so you have set, and then you try X to be as close to set as possible. So on top of the data fidelity term and the regularization, now you have this constraint you are trying to enforce, in which X has to be similar to set. And yeah, the regularization parameter has to be larger than 0. And if you make it too large, then you are back to this problem, because you are forcing strictly that X is equal to set. If beta is a relatively small number, then this will be enforced, but not, that will be a soft push towards X being equal set. Okay, so then we have modified our problem, and then we will alternate between first minimizing X and then minimizing set. So when you have the X problem, or the X problem, this R does not depend on X. So you can take it out, and then here we have a fully quadratic problem that can be solved analytically or with gradient descent or whatever. So first, given the set, you update your X, and once you have updated your X, now you update your set, and set, you have the quadratic term that is it is fully differentiable, plus this one that is not differentiable, but then you have the proximal operators. And the proximal operators, we have seen that they are relatively simple. So for instance, for L1, this is the proximal operator for L1. Okay, so this is not a universal proximal operator. This is only applies to L1. So every penalization term has its own proximal operator. You need to know which one it is. And yeah, I think that's all. And this kind of structure is also very much used in ISTA, FISTA, that again, in image processing, they are very much used, and ADMM. Any question?
How do you know which is the proximal operator?
We will present it now, I think, in some, did we yesterday? Did we do the yesterday? Yeah, so the proximal operator, so let's say that you have a function g. I think I read this slide. Thank you. So yeah, this was the my setup that I did in the whiteboard. So this is this proximal and operator splitting algorithms. They apply to this kind of problems where f is differentiable and convex, and g is convex and non-differentiable. And there is an alternation. I will come to your question, okay? But let me. So there is an alternation between doing a gradient descent and then projecting using the proximal operator. And these are also called forward-backward splitting. So the forward is the part of the gradient step, and the proximal operator is called the backward. So how do you know what is the proximal operator? So the proximal operator is a function that you see it has an argument v, but here your goal function has x and b, but you are minimizing an x, so you are eliminating the dependence on x by the minimization. So the whole thing only depends on v. And then let's look at the goal function. So the goal function is the part that is non-smooth plus 1 over 2 lambda, and then for this vector, you try to find the x that is as close to v as possible in a quadratic sense, and so that the whole thing is minimized. So this is the definition of the proximal operator. How is it that for L1 you come down to this one? That is more difficult to show. But the definition is clear. The definition is this one. Okay. And typically you don't get for any GX. So GX there are a few regularizers that are useful, and for each one of them, someone has worked out what is the proximal operator. Any other question? No? Okay. Okay, so then let's move on to the next family of algorithms. These are called prime and dual problems, or prime and dual algorithms. So let's start with the standard problems. We have minimization of f, and then subject to some constraints, inequalities and equalities. And this is called the primary problem. The dual problem is the one that minimizes the Lagrangian. So you put all the constraints with their own Lagrange multipliers, and you construct this function and you try to minimize this function. There are some constraints. The multipliers associated to inequalities, they have to be larger than 0, and the multipliers associated to equalities, they are free. So they have to be real numbers, but they are free to take positive or negative numbers. Very good. Then we construct the dual function. So the dual function is a function that depends only on lambda and v. So the Lagrangian depends on x, lambda, and v, but if you minimize over x, then you have removed the dependence on x. So it only depends on lambda and b. We will see an example, so it becomes more clear. So this dual function, it gives a lower bound on the optimal value of the primal. So the primal, it is like this kind of here you have x, here you have f, f is like that, and then the dual is something can be like this. So this is primal, this is dual, this is primal. The dual is said to be a lower bound. They can touch or not or whatever. So it is always below the primal flow. Okay, so this is a lower bound, and the reason is because here you have something negative. So this is negative. This is lambda is positive. So it is the function plus something that is negative always, or at most. So in the best case, you are in the border of the boundary, and then this is zero. So either it is zero or it is negative. So it is the function plus some negative number. So that gives you a negative number. So that the whole Lagrangian multiplier is always lower than f. Okay? And this will be zero. Once you have satisfied everything, this is zero. So that is why it is a lower bound. And then we haven't solved it yet. So we have this problem, construct with the dual function. Then we have reasoned that the dual function is a lower bound of the original function. And now we will maximize the dual function over this this constraint that the lambdas have to be larger than zero. And it turns out that this problem is always concave. So always. So that is so even if the original problem is not convex, the dual optimization is always convex, concave. So it is relatively easy to find the maximum. Okay, so let's give an example so that it is less abstract. So let's start with this primary problem. So we want to minimize the distance to the number 2, subject to the constraint that it has to be between 0 and 3. So actually, this is a very simple problem. So what we have is have x, then we have 2, 3, 0, this is x, and we have a parabola here, and this is x. And we want to find the minimizer. Yeah, the minimizer is obviously 2. But let's see if we can find it with this technique. Okay, so the first thing is to rewrite the constraints in inequalities that are smaller or equal to 0. So this one will rewrite this way, and this one will rewrite this way. And then we construct the Lagrangian. Okay, so the Lagrangian is the function plus lambda 1, the first function, the first constraint, plus lambda 2, the second constraint. Very good. So we have here the Lagrangian. Then we have to construct the dual function. So the dual function, remind, it was this one that was minimizing the Lagrangian with respect to x, given all the multipliers. So you have the multipliers, so you have the Lagrangian, you expand it. We can write it this way. So it is x squared plus some coefficient times x plus some constant. And then we compute the derivative set to 0. So the derivative of this is 2x, the derivative of this is just the constant in front, and then set to 0. So the optimum value of the Lagrangian given lambda 1, lambda 2 is this one. So now we have the dual function because we only have to substitute this thing into the Lagrangian. Okay, so we'll do that. So we substitute this thing into the Lagrangian, and this is what we are doing here. So it is x star minus 2 squared minus lambda 1 x star plus lambda 2 x star minus 3. You manipulate this a little bit, and then you have something that does not depend on x. This is what I said at the beginning. So once the Lagrangian depends on x, lambda, and nu, but if I minimize over one of the variables, the function, the whole thing, does not depend anymore on that variable because of the minimization. So the dual function here does not depend on x. It only depends on lambda 1 and lambda 2. Okay, and now we have to maximize it. We have to maximize it subject to this constraint. So if we want to maximize it, we compute the first derivatives. So the derivative of the dual function with respect to lambda 1 is this one, with respect to lambda 2 is this one, we set to 0. From the first equation, you have that lambda 2 minus lambda 1 has to be equal 4. From the second one, you have that lambda 1 minus lambda 2 has to be equal 2. And if you solve this equation system, there is no solution. And you see here lambda 2, if you multiply by minus 1, you have lambda 1 minus lambda 2 is minus 4. And in the second, lambda 1 minus lambda 4 is equal 2. So there is no solution there. Okay, so there is no solution that is larger than 0. Okay, so in the interior part, so if you think in the lambda 1, lambda 2 space, so here we have lambda 1, lambda 2 space. In this area, not the borders, okay, but in this area, there is no solution. Okay, so there is no solution. So it must be that our goal function somewhere here. Okay, so this is our goal function, and then we have to look at the borders. Okay, so we have to explore this area. So the unconstrained problem doesn't have a solution. So we have to look at the constraint problems, and to evaluate the constraint problems, we will take a few points here and see how the function looks like. Okay, so we will look into the boundary, and then we try some of the boundary points, not all the boundary points, but we try a few of them. So lambda 1 equal lambda 2 equals 0. So we explore the corner. There the function is 0. Then we take 1 and 0. It is minus 2.25. We try 0.01. This is not even in the boundary. This is in the middle. Okay, so we try a few points, and if you try many more, it turns out that the maximum is this one. So now we know that lambda 1 is equal to lambda 2 is 0. So that is the maximizer of the dual problem. So we have found the maximizer of the dual problem. So now we come back to the goal function, and the goal function. So here. So if you give me lambda 1, lambda 2, the best x is this one. So this we already solved at the beginning. So, but we know that lambda 1 and lambda 2 are 0. So the best solution for this combination of difference is 4 divided by 2, that is 2. And so now we have that the maximum of the dual function is 0, and so our Lagrangian, these two terms disappear, and that means the two constraints are not active. So in this problem, we have two constraints. One constraint is this one, so you have to be there. The other constraint, or you cannot be there. The other constraint is that you cannot be there, and the solution is not touching the constraints. So none of the constraints is active, and that is the meaning of this lambda 1, lambda 2 equals 0. See? None of them is active. And then so you are in an unconstrained problem, and you could solve it again, or you already know the solutions because you have found, given lambda 1, lambda 2, what is the best x for that combination of lambdas. Any question? No? Okay, so let's move on to the next family of methods. And this family is called these decomposition methods. So the decomposition methods, they apply to different kinds of structures. So you have seen the flow that we have been the structure of the lecture. So we started with a problem. Minimization of f, subject to a number of constraints smaller than or equal to 0, a number of constraints equal to 0. Then we have seen general techniques. General techniques are the ones based on gradient descent that we saw yesterday. So we saw yesterday these general techniques. Today, what we are seeing are specific techniques. So these are specific techniques. We have started with the proximal and splitting. It is for problems that can be formulated in this way. And the ones that we will see now are the decomposition, that are for problems that can be formulated in these ways. So one is in which there is a sum of different functions. So the goal function is a sum of other functions. And each of these functions can be handled separately. So we will see an example. And the other one is this variable decomposition, in which we have a sum of two functions, and these two functions, so one depends on x, the other one depends on z, and then x and z are coupled through some constraint, some equality constraint. Okay, so these are the techniques that we will see: dual decomposition, primary decomposition, ADMM that we will see next lecture, and the block coordinated method. Okay, so these are the characteristics of each one. This one is a summary of what we will see. So we need to see the summary. So let's start with this dual decomposition. So here you see you are minimizing a function that depends on x1 and x2, but the dependence is f1 depends on x1 and f2 depends on x2. So in the formulation we had before, here, if we have a long vector, it is like you have this f of x. You have this f of x. X is a long vector. It's a vector, many components. But this part of the vector, that we will call it x1, is evaluated, separated from this part of the vector that we will call it x2. Okay, so this is this structure that we mentioned here. So you have a goal function that is a sum of goal functions, but this sum of goal functions, they apply to different parts of the vector. So, and the two vectors are coupled by some constraint. Okay, so we start by formulating the Lagrangian. So we have f1 plus f2 plus the constraint. And then we construct the dual function. So the dual function, there is only one constraint, so it depends only on one multiplier. And it is the minimization of this thing with respect to x. But the minimization of this thing with respect to x, you can separate into different components. So this part does not depend on x2, so you can minimize separately. This part does not depend on x1, so again, you can minimize separately. And this part does not depend on x1 or x2, so there is no way to minimize that. Then, now, if you think in a distributed system, so this problem will be solved by one agent. This part will be solved by another agent. And the agents, the only thing that they need to know is the lambda, because this thing only depends on lambda and x1, and it is minimizing on x1, so it only depends on lambda, and the same for this one. So once you give lambda, this agent can solve this problem. This agent can solve its problem, and they can be done in parallel. Okay, and so minimizing this, each one of these, we saw an example here. So we had an example in which each one of the dual functions at the end, each one of the dual functions will give us a given lambda. Here in the example, it was lambda 1 and lambda 2, but given lambdas, I will give you the best x1, and the other agent, given lambda, it will give you the best x2. Okay, so now, where are we? We are here. So these two, given lambda, will give you the best x1. Given lambda, it will give you the best x2. And now x1 and x2 depend on lambda. So now you have something that only depends on lambda. This is what this is saying. x1 star that depends on lambda, x2 star that depends on lambda. These are the minimizers of these two dual functions. And we have to compute the gradient of the dual function with respect to lambda. So this does not depend on lambda. This does not depend on lambda. And the gradient of this function with respect to lambda is just this coefficient. So, but this coefficient, it depends on lambda. x1 star depends on lambda, x2 star depends on lambda minus c. But this is coming from here. So it is the derivative of the Lagrangian with respect to lambda, which is very easy to compute. And then you can use whatever method you want. So set this to 0 or gradient descent or whatever. So you find the best lambda. Once you have the best lambda, you have automatically x1, the best x1 and the best x2. Okay. And the thing is that this thing can be solved in parallel. You can split the problem into two sub-problems that might be easier to solve. Any question? No?
Can we see an example of this? Like an actual problem or?
We may try later, but yeah, so they don't look too different from these ones. I think that the most from this one that we saw here, only that this function is that this was a scalar, but if it is a vector, then you could have two separate parts. The thing is, in which kind of problems, in which real life problems, not that these mathematical things, in which kind of problems these kind of decompositions appear. And in image processing, I'm not so sure. Maybe one of these ISTA or VISTA, they have formulated like this. But I think it is an interesting question for you. Because solving this, so solving an example like this one, here, that, okay, you can do the mathematics, but at the end, it's a mathematical exercise. I think the real stuff is in the real life. So it is something for research, I don't know. Okay. But actually, next hour you may try to see in which real life problems this kind of methods are will be interesting. And you can present it, it can be one of your practices. Very good. And then, what is the, where are we? I think we are there. Okay, so I got lost. We were here. This we saw. Yeah. So we are here. So here you have an example, but again, it is a kind of artificial one. So I think the real stuff is in real life. So let's say that you have this primal problem, and one is x1 squared, this one is x2 squared, and they are subject to some constraint. So you construct the Lagrangian. And given this Lagrangian, we can construct the dual function, and the dual function is you reorganize this thing with everything that depends on x1, everything that depends on x2, and then this minus lambda that stays alone. Then you solve the two dual problems independently. So the solution of this one is x1 star minus lambda. The solution of this one is x2 star minus lambda 2. And then the dual function, if you substitute here again, so this is the value. So this is the value, x1 star is minus lambda, but you have to substitute minus lambda here. So it is minus 1/2 of lambda squared. So this is, all this thing is minus 1/2 of lambda squared. All this thing is the same. And then you have the minus lambda. Then we have to maximize this. So we maximize this. And you can use a gradient descent, for instance, for that. And the gradient descent at the end converges to lambda minus 0.5. And if lambda is minus 0.5, you substitute here, x1 and x2 are 0.5. And that is the optimum of your primal problem. So here you have the example you were asking. But again, these are mathematical exercises. I don't find them so interesting.
So are we going to do any mathematical exercise in the exam or something like that?
No. So at most, what I will give you is a solve exercise, and then you have to interpret your seeing that. So here we have another way of solving this kind of problem. So let's say that we have the same formulation. So we have a goal function that the first part depends on x1, the second part depends only on x2, and they are coupled. So what you can do is you fix one of them. So let's say that you say x1 is s. Okay. So if x1 is s, because of the constraint, x2 has to be c minus s. So now you substitute into the original problem. This is called a reparametrization of the original problem. So now everything depends only on s. So it is a one-dimensional problem, or one-dimensional, the same dimension as x1. So here, let's say that we have the same example as before. So this is the part that depends on x1, the part that depends on x2, and the constraint. So we introduce we fix x1. Once x1 is fixed, because of the constraint, you have x2 that is fixed. And then you substitute into the original problem. So you have 1/2 of x1 squared plus 1/2 of x2 squared. And then you solve this the best way you want. So this is just some operations. You compute the derivative of this thing. This and this is the same. So you compute the derivative of this with set to 0. So the derivative is 2s minus 1 set to 0. S is 0.5. So now you know x1 and you have x2. But again, these are mathematical exercises, not so interesting. So the interesting thing is in which kind of real life problems these prime and dual decompositions apply. I think it's very interesting research, hopefully. Any question? No? So let's stop here with the theory today. And we continue with our notebooks.